Welcome to BCIS 3347. My name is Dr. Schuessler, and today's topic is Chapter 4, TCP IP. So if you're in our course shell here, you can go ahead and scroll on down over here to the left-hand side in our navigation structure. You can see the slides link is right there, and when you click on that, it'll open up a shared Google folder. All the slides that I have for this semester for the text that we're using are posted right in here. So we're covering today Chapter 4, Introduction to TCP IP Protocols. So I've already got it open here, so let's go ahead and put that in presentation mode and jump on in. So as I said, Chapter 4, Introduction to TCP IP Protocols. So the objectives for this chapter are to identify and explain the functions of the core TCP IP protocols. We'll explain the TCP IP model and how it corresponds to the OSI model. For the most part, it's pretty simple when you see it here in a few slides. I think you'll be able to see intuitively how those different layers relate to one another. We will discuss addressing schemes for TCP IP in version 4 and version 6, and we'll talk about how addresses are assigned automatically using DHCP, or Dynamic Host Configuration Protocol. We'll describe the purpose and implementation of DNS, Domain Name System. We'll discuss well-known ports for key TCP IP services. There are literally thousands of different port numbers that are used by various applications, but we're just going to focus on some of the main ones that you should probably be aware of. And we'll finish up talking about common application layer TCP IP protocols and how they're used. So before we jump into the rest of this, let's talk a little bit about what a protocol suite is. A protocol suite refers to a collection of protocols that all work together to be able to help a message move from point A to point B. So when we go back to our OSI model that we've talked about previously, as a message gets encapsulated going down the different layers of that model, it's going through these different protocols that are all working together with the common purpose of delivering that message from the sending machine to the receiving machine. And because they're all working together, all working in unison, it's referred to as a protocol suite. It's a collection of protocols that are working together for that common purpose. Now, when we talk about the TCP IP protocol suite, we talk about these for a specific reason. It's a very popular suite of protocols because they tend to be open in nature, so they don't cost anything to use. They're flexible. They run on a lot of different platforms, specifically TCP IP. Runs on Windows, runs on Macs, runs on Linux machines. So it's very flexible, runs on lots of different operating systems, and allows different systems to be able to communicate with one another. And they're routable, which means we're able to now connect different networks together and send messages across those different networks. So it's suitable for large networks like the internet. Now, the TCP IP model is very similar to the OSI model, except instead of having 7 layers, it has 4 layers. And the next slide we'll see how those layers relate to each other, but it's really pretty intuitive, I think. There's the application layer, which is the layer that's closest to us as an end user. It's not the software application that we see that we're actually interacting with, but rather it refers to the protocols that application is actually using. So when we go to use our web browser, we use Chrome or Firefox or whatever browser that it is that we happen to be using. We're not talking about the application when we're talking about the application layer of Firefox or Chrome. We're referring to the protocol that's used, usually HTTP. The transport layer is the next layer down, and this is what actually breaks messages up and sends them on their way. There's the internet layer, which is responsible for routing and provides us with addresses for each packet so that it can be properly routed. And then lastly, there's the network access layer, where that's really kind of the layer where we start to put messages on the wire, or we broadcast them through radio waves. So that's kind of a look at the TCP IP model in a nutshell. here's how it relates to the OSI model. So you'll see that in the TCP/IP model, they've condensed the application, presentation, and session layers down into one single layer, and that's probably pretty appropriate. Most of the time, your software applications combine those different functionalities together into one product and take care of all three of those issues in that software application. The transport layer is pretty much the same. The internet layer in the TCP/IP model is pretty much the same as the network layer in the OSI model. And then the TCP/IP model combines the data link and physical layers of the OSI model to represent the network access layer in the TCP/IP model. And you can see some of the protocols and services that are offered at those different in each one of those different layers. So HTTP, FTP are common protocols that are used at the application layer. TCP, UDP are common protocols used at the transport layer. IP, ARP are commonly used at the internet layer, and then Ethernet is commonly used at the network access layer. So we talk a lot about TCP/IP because this is the language of the internet, if you will. It works with other protocols, but these are the two ones that we really like to focus on a lot because it's responsible. They're responsible for doing a lot of the heavy lifting on the internet. They operate at the transport and network layers of the OSI model respectively. TCP at the transport layer, IP at the network layer. They provide basic services to protocols in other layers. So they're working with the layers above and below those two layers. And the two protocols that work at these, most of the time, the most significant ones are specifically TCP and IP. These are two different protocols, but it's referred to as a protocol suite because they work so closely together. So the transport layer, TCP specifically at the transport layer, provides for reliable data delivery services. So we're not talking about the transport layer at this point, we're talking about TCP specifically. So this protocol specifically provides for reliable data delivery services. What do we mean when we say reliable? It means that our packets are going to get there. They're going to get to where they're supposed to be going. We feel confident that that's going to occur. The data that actually arrives is the data that was actually sent. So we do things like checksums to verify that the data sent and the data received are the same. Sequencing is involved. In other words, remember when we talk about sending data across the internet, we break up a larger message into smaller chunks to be able to send it across the network. When we do that, if it's important that they be reassembled in the same order, in the proper order, we need to have some sort of order to each one of those packets so we can reassemble it. That's where sequencing comes in. Now, also, TCP provides for flow control. So just because a sending side can send at one speed doesn't mean that the receiving end can receive at the same speed. So basically, when we establish that connection, remember it's a connection-oriented protocol, that when the sending end and the receiving end are establishing that connection, they negotiate the speed with which they can communicate. And basically, they're only going to communicate at the fastest speed that the slower end can communicate. So that's what flow control is about. If we didn't have flow control, you might run into a problem where packets start getting dropped because the receiving end might not be able to process as much data as the sending end can send out. So it simply becomes, backed up with too much data coming in. And then TCP is responsible for segmenting the different parts of the packet. And we'll see that here in the next slide here. So here's what a TCP packet looks like. And you can see there's a lot of different pieces to it, a lot of different parts to it. So the next few slides actually kind of talk about some of the details of this. The important things that I want you to really notice are things like the source port, the destination port, the sequence number, and the data checksum and the data down here. So for source port and destination port, these are things that get combined later on in the next layer with an IP address to be able to create what's referred to as a socket. And we'll talk about those a little bit later in the presentation. But the port numbers are important. If you send in a request to a server, that server is going to look at the port number that's coming in, and that's what's going to tell it which application to respond to that request from. So for example, when you have a destination port, when you have a port that comes in on the server side and it sees port 80, that the request is coming in on port 80, the server knows, oh, that's a web request. I need to respond with my web server to be able to respond with the appropriate application, as opposed to trying to respond with an email response or something like that. Sequence number, again, is important in terms of being able to reassemble messages together. Checksum to make sure that the data sent and the data received are the same. And then lastly, our actual data itself that we're really interested in seeing. So all of this other stuff is just overhead. Our data is the actual data that we're really interested in. So there's a lot to a TCP packet. And so this kind of goes into a little bit more detail about what each part of a TCP packet includes. As far as the process for establishing a TCP connection, remember we talked about it being a connection-oriented protocol. Basically, on the sending side, the part that's really interested in establishing the communication, let's say it's a client computer that wants to request web pages from a web server. That client sends a message to the web server and says, "Hey, I want to set up a connection." So it sends a segment with a SYN bit set to the server to establish a connection. That server is going to respond with what's referred to as a SYN ACK in response to that request. In response, the client's going to again send a SYN to computer B or that server to finish establishing that connection and say, now we can go ahead and communicate. Everything else after this is related to our specific message. We've got that connection established. Once we're finished, we send a FIN, send another segment with a FIN flag set, and that's what's going to indicate that the transmission ends. Now, if we wanted to bombard a server so that it has so many requests that it can't respond to legitimate requests, we never close those transmissions. We never finish this initial handshake, in fact. We send the initial SYN, we receive the SYN ACK back, we never send the next SYN back. And as a result, we create a problem for that web server and inhibit its ability to respond to legitimate requests. So here's what it might look like graphically. Now, TCP is not the only protocol that can be used at the transport layer. UDP is another common protocol that's used at the transport layer. Unlike TCP, which is a connection-oriented protocol, UDP is connectionless. It does not go to the trouble to set up a connection before it starts transmitting. Because it just starts transmitting, it really doesn't have any kind of idea about flow control. It doesn't really have any kind of idea about sequencing or the quality of a message or the quality of a circuit or anything like that. It simply sends the messages and assumes that the network is in good enough shape that messages are going to get where they need to get to. So there's no assurance of packages received in the correct sequence, no guarantee that the packets are going to get there at all. There's no error checking, no sequencing. It lacks sophistication, but that's not necessarily a bad thing. That lack of sophistication means that it tends to be a little bit more efficient than TCP, or perhaps quite a bit more efficient than TCP. And that comes into play in certain situations. So say, for example, we're trying to stream audio or stream video. We don't want to go back and play older messages. If we have a few bits that are out of order, we don't want to replay those. We want to just keep going. So when you hear a little bit of that jitter in a voice communication or something like that, that's why we're using UDP. The speed is more important than going back and playing some missed bits. So here's kind of a reflection of that lack of sophistication. So you see we have a lot less overhead when it comes to UDP. We have source port, destination ports, the length of it, and then the data. So the data makes up the majority of a UDP packet. Now let's go ahead and move down a layer. Let's look at the internet layer. So the IP, or Internet Protocol, is typically what's going to be used at this layer. So the network layer protocol really addresses the how and where data is delivered. So it really deals with the source address and the destination address. So in the previous one, when we were talking about transport, we were focused on ports. When we're talking about the network layer, we're focusing more on addresses, so like an IP address. So this is what enables a TCP/IP network to inter-network or send messages from one network across the internet to another network. So it allows those messages to traverse more than one LAN segment. Network layer data is formed into packets. An IP packet has a data envelope, so we encapsulate the message from above. We encapsulate that transport layer message from above into a data envelope, and it contains additional information or overhead, which provides routers information to be able to forward those messages to other LAN segments. Now when it comes to IP, there's two basic versions that are in use currently. There's IP version 4, which was developed in the 70s and formally introduced in 81. Has about 4.3 billion addresses, which seems like a lot of addresses. They're not all usable addresses. They're not all routable across the public internet, which reduces some of those. Some of those are reserved for special things like multicasting or private IP addresses for the internal addresses of networks. And so as a result of this, we have fewer than 4.3 billion addresses. We have more than 4.3 billion people on this planet. We also insist on hooking up everything from coffee pots to our thermostats to refrigerators, cell phones, etc. to the internet. So as a result, we've managed to burn through most, if not all, of those addresses. Depending on the news source you read, we're currently out of IP version 4 addresses. So there was this push, and has been this push for some time, to develop a new version, version 6. It was introduced in '98. We've been pretty slow to adopt version 6 because there's been ways to extend version 4 for most of our needs. But slowly over time, we will continue to move towards version 6, and it provides us with a number of advantages. First obvious one of which is the vast increase in the number of addresses possible. And I don't even want to go into what that number is, 3.4 times 10 to the 38th power. It's a significant number of addresses. Some of the advantages to version 6 provides billions of additional IP addresses, but also provides better security and prioritization provisions. So for IP version 4, it was really IP was really kind of a proof of concept. It was about developing a system that was going to be very resilient and help us to communicate. Security was an afterthought. It was a band-aid, if you will. And so the security that we have on the internet was not part of the original design. It was something that was done after the fact, and I think we've done a pretty good job with that, but it's not ideal. IP version 6 was designed from the get-go with the understanding that better security needed to be designed into our IP layer protocol, and so IP version 6 does that. It also does a better job of prioritizing data, so it allows us to say certain types of data needs to get priority over other types of data. So video and voice, for example, needs priority over something like email, where a few second delay is not a big deal. But when it comes to voice communication and video communication, a few second delay is a big deal. It significantly impacts our message. So an IP version 4 packet is going to look something like this. We're going to start off with a version. The version's simple. We just got through talking about it. Is it version 4? Is it version 6? This is what's going to tell the receiving end what version of IP is being used. There's several different other fields that we see in an IP packet. Source IP address, destination IP address, so where it's being sent from, where it's being sent to. time to live. We want these packets to eventually at some point die. We don't want to get into a situation where IP packets are bouncing all around the internet forever. So eventually we kill those packets off, and that's what time to live basically does. And then the part that we're most interested in is, again, our data. So this whole thing, all of this overhead is designed to get our data from point A to point B. Version 6 looks a little bit different, looks like a lot less overhead. We handle a lot of this stuff up in here, our source address, destination address, etc. Okay, so ICMP is another protocol that operates at the network layer of the OSI model. It manages multicasting on networks running IP version 4. So what is multicasting? Typically we operate in a point-to-point communication. We establish a connection from our client to a server. That's a point-to-point connection. We get our data, we're done. But there are situations where we might have point-to-multipoint transmissions, and that's where multicasting comes into play. One node sends data out to multiple nodes or groups of nodes. And this is good for things like teleconferencing, video conferencing, in some cases if you're familiar with lab environments and the need to re-image multiple machines all at once. You can either across your network update each individual machine, but now you're tying up a bunch of bandwidth, or you can multicast, and that way it's basically using the same data just once going across that network connection. ARP is another network layer protocol used with IP version 4. This is what allows us to resolve MAC addresses to IP addresses. It basically creates a database that maps the MAC address to the IP address. An ARP table is maintained on the client, and this is what keeps track of those different addresses and helps to increase the efficiency of communication on a local segment. ICMP, Internet Control Message Protocol, is another network layer protocol that's used. Reports on data delivery success or failure. It announces transmission failures to the sender, such as network congestion, data fails to reach destination, data discarded, such as the time to live expiring. So this is something that routers use basically to check connections. You can use your own when you implement or when you use the ping command. You're sending out an ICMP packet that goes across the network to check a connection. So IP version 4 addressing. Networks recognize two kinds of addresses, logical and physical. When we're talking about logical ones, we're talking about IP version 4 or IP version 6. This is a logical layer address that's assigned at the network layer. And I say assigned because we as users have the ability to assign those addresses. It may be dynamically assigned, we'll talk about that a little bit more here in a little bit, through a DHCP server, but it's something that we configure as a user or as a network administrator. This is as opposed to a physical layer address, the MAC address or hardware addresses. Those, while in some cases can be assigned, typically are hard-coded into the network interface card, the NIC card. The IP protocol handles logical addressing, so that's what we're focusing on here. IP version 4 is a unique 32-bit number, and it's divided. We don't like to remember long, great big long numbers, so instead of using 32 bits of zeros and ones, we like to break those up into smaller groups, or when it comes to IP, 4 octets. So when you see those addresses 144.92.43.178, those are 4 octets. Each group is an octet. 4 of them combined represents our 4 octets. And these are representations. When we combine all of these, if we converted these to from decimal to binary, it would be 32 bits. So some people refer to this as dotted decimal. The network class is determined from the first octet. In other words, this octet right here will tell you which class that it's actually associated with. So if that first octet is 1 through 126, that means we can have 126 different networks. On each network, we can have 16,700,000 different hosts on that one network. And this is a Class A network. So when you see anything between a 1 and 126 for that very first octet, that tells you you're operating as a Class A network. Class B are 128. Notice that there's a skip between 126 and 128, and we'll come back to that here in a little bit. So 128 to 191, that's a Class B network. We can have a lot more networks in a Class B network, but the number of hosts that are available on a Class B network, on each Class B network, is significantly fewer. A Class C, which is typically what you're going to see on a home network, operates from 192 to 223. Lots and lots and lots of networks, far fewer hosts per network. So again, when you see the first octet beginning with these numbers, that's going to tell you what class network you're working in. Now there's other classes, Class D, Class E, for example, and these are really very specific classes for specific situations. Class D is for multicasting, Class E for experimental use. For the most part, you're never going to work with Class E. Class D you may work with in very few situations, but not particularly common. But you'll notice that those address spaces are just a little bit different. So each octet has 8 bits. If you do your little translation of bits, you'll see that you end up with 256 combinations. So if every bit is set to 1 and you convert that to decimal, you end up with 256. Now that doesn't mean you can have 256 hosts connected to that segment. Networks use 1 through 254. So the very first bit is 0. It's 0 through 255. So 0 is reserved as a placeholder. That refers to, that's a generic reference to that network. So if, for example, we have 192.168.0.0, that refers to the 192. Let me back up here for just a second. I'm getting confused. 192.168.0.0 refers to that 192.168.0 network. So anything else is on that network. Typically, your default gateway is going to be 1. It doesn't have to be, but that's typically going to be 1. 192.168.0.255 is a reserved address also. It's used for broadcast transmissions. So when a computer on that segment doesn't know the IP address of another computer that it needs to communicate with, it sends a broadcast message to 192.168.0.255 to say, hey, who's got this IP address? And the appropriate computer should respond. So Class A devices, they're going to share that same first octet, bits 0 through 7. So that's 8 bits, 0 through 7. And those first 8 bits represent the network ID. That network ID says, if that network ID is the same for 2 computers, that means you're on the same segment. You're able to actually talk to each other. If those bits are different, you're on a different network and you won't be able to communicate with each other unless you've got a router involved. The remaining bits, 8 through 31, represent the individual hosts. So again, on a Class A, you've got 8 bits for your first octet and the remaining bits for your host. So you have few networks, lots of hosts. Class B is a combination of the two. It's kind of in between. The first 2 octets, 0 through 16, or 0 through 15, represent the network, and the hosts are the second 2 octets. So you end up with a compromised shared number of hosts and networks. And then Class C, the first 3 octets, 0 through 23, represent the network. Again, if all of these bits are the same, you're on the same segment. As a result, all the clients on that segment can talk to each other. If they're different, you need a router to be able to communicate between those two computers. So graphically, here's kind of how it looks like. Class A, Class B, and Class C. Now, if you recall from a few moments ago, we talked about that one address that was missing, 127. That's referred to as a loopback address. When the first octet equals 127, this is a loopback address that allows you to do some troubleshooting. So on your individual machine, if you happen to have, let's say for example, let's come over here and open up a command prompt that I want to be able to do some troubleshooting. One of the things that I can do is open up a command prompt, and this will allow me to do some of this troubleshooting. Excuse me. So if I want to start to test my communications, I can do a ping 127.0.0.1. So I ping, and I get this kind of information back. I get a reply from this address, time to live, all those kinds of information. No lost. That's a good thing. That tells me that my local protocol stack is working properly. But I want to get out of there. I want to find out a little bit more information. I want to ping, say, Google. So when I ping Google, it tells me a couple of things. Number one, because I typed in not the IP address, but the domain name, it resolved the domain name, which tells me the DNS server is working properly, and I was able to connect to it as well. So this is that ICMP packet that we were talking about earlier. So that's one example of why you might use the loopback address. In reality, 127 dot anything else, any of these other valid numbers, will result in the same results. It's just that first 127 designates it as being a loopback address. So loopback test, that's basically what we're doing. We're testing the protocol stack on our local computer to make sure that it's functioning properly. Something else before I go back to the presentation alone is ipconfig and ifconfig. They're basically the same thing. ipconfig allows you to check some of your configuration information on your computer. Same thing for ifconfig in the Linux environment. So over here again with our command prompt, if I type in ipconfig, I will get some basic information. So let me actually expand this out just a little bit. So here I've typed in my command, I'm getting some information back. I get my IP address, my subnet mask, my default gateway, and so on. Something else that's sometimes useful is type in ipconfig. Now I want to use a switch because I want all the information I can get. So I put in the /all, and now it's going to give me more information than what I initially started with. So now I can tell the host name that I've got, primary DNS suffix, is routing enabled, what's my DNS server, MAC addresses or my physical addresses, stuff like that. So I get a lot more information when I do something like that. Is DHCP enabled? So this is some useful information, especially when I start to get down to troubleshooting and stuff like that. So those are some basic utilities that will crop up later on in the semester. So let's go on back into our presentation here. So those dotted decimals that we're talking about are really just representations or decimal representations of binary digits. So those digits can only be represented 0 through 255 because if you do the conversion, that's the max that you can go up to. If they're all zeros, if all those binary digits are all zeros, then the binary or the decimal equivalent is 0. If the binary numbers, all 8 bits, are set to 1, we end up with 255. So it actually gives us a representation of 256, 0 through 255 in decimal. Dotted decimal addresses have that binary equivalent. We convert each octet and remove the decimal points. So One of the other important parts of our configuration is not just the IP address, but also the subnet mask. And why is the subnet mask important? Well, it tells us which part of the IP address refers to the network versus which part refers to the specific client that we're working on. It looks a lot like an IP address. It's a 32-bit number identifying the device's subnet. It's combined with the with the device's IP address to determine whether or not you're on the same segment or not. It informs the network about the segment and the network where the device is attached. Like the IP address, it's 4 octets, 32 bits, expressed in binary or dotted decimal notation. And it's assigned the same way that IP addresses are assigned. You can either manually type them in, or it can be assigned via the DHCP server. So for a Class A network, remember your IP address is going to be 1 through 126. The default subnet mask is 255.0.0.0 for your subnet mask. This is going to tell it anything that's on the same network, any of them that have the same default subnet mask are going to look for this very first octet to determine if you're on the same network segment. For Class B, the default subnet mask is 255.255.0.0. Again, the same thing. When it sees this, when your computer sees this, it's going to look for other computers. It's going to tell this computer to look for other computers that have the same first 2 octets that are identical. And then Class C, the same thing. The first 3 octets. If the first 3 octets are the same, they're on the same network segment. Now, IP version 4 is a little bit simpler than IP version 6. That's just because that's the nature of the beast. Much fewer numbers, much easier to kind of conceptualize. A lot more bits for IP version 6, and this is what allows us to have so many more addresses, but it also adds to the complexity and adds to potential confusion. So 128 bits, we use 8 16-bit fields, so it looks similar to a hexadecimal, or it looks similar to a MAC address. It's not the same, it's much longer, and the groupings are a little bit different, but it looks very similar to a physical address or hardware layer address. So they're in hexadecimal rather than binary or decimal, separated by a colon. So here's an example of an address that you might see. Pretty long address, difficult to remember. Now there are certain abbreviations that you can do. So for example, if we see a situation like this, we can actually remove these 2 zeros, and that's what they're talking about here. We can abbreviate that with just FF. We can also go and look and see certain situations like this, and we can abbreviate that as well, so we don't have to type everything out. IP version 6 also has a multicast address used for transmitting data to lots of different devices simultaneously. They also have what's known as an anycast address, which is similar but not quite the same. It has some subtle differences. To be honest with you, I'm not that familiar with anycast addresses. Modern devices and operating systems can use both IP version 4 and IP version 6. It's been a standard part of Windows. Version 6 has been a standard part of Windows for quite some time now, even though it's not used an awful lot just yet. Now, how do we go about figuring out what our IP address is and things like that? Well, it really depends on the layer that we're talking about. For the most part, as end consumers, our router is assigned an IP address from our ISP. But where does our ISP get them? Well, they get them from government-sponsored organizations that dole out these different addresses. Some of these organizations are IANA, ICANN, RIRs, etc. And these are different organizations that are spread in different parts of the world, and that's their job, is to dole out different IP addresses to different groups. So they dole these out to companies and to individuals. And usually these companies are going to be large corporations or ISPs of some nature. Every network node has to have a unique IP address. So on a particular segment, if you've got the same IP address as somebody else, there's going to be a communication problem. You're not going to get all the packets that are addressed to you. They're not going to get all the packets that are addressed to them. It's going to be a problem for those computers. So every node has to have a unique IP address. So how do we go about doing that? Well, we can either statically assign them or we can dynamically assign those IP addresses. If we really want to make sure that we don't have duplications of IP addresses, we're going to use dynamic IP addressing. This is basically, we'll have a dynamic DHCP server on our network. Usually, especially in the home environment, our wireless router takes care of this for us. It has a DHCP server built into it, but there's other DHCP servers that are available, and this keeps track of the IP addresses that are being assigned dynamically to the various hosts that are on the network. There are other dynamic protocols that are out there, configuration protocols that are out there. DHCP, though, is by far the most common. We can also statically assign addresses, and this is where we manually go in and configure a client or a server with a specific IP address. There are reasons to do this. We may have certain devices that we do not want the IP address to change. Servers, for example, we don't want those IP addresses to change. Printers, network printers, we don't want those IP addresses to change. So typically we want to statically assign those an IP address so that it doesn't change. Now, depending on the DHCP server that you're creating, in some cases you can set the server to actually assign those devices the same IP address all the time. But that's typically not something you're going to see in a consumer-based router. Windows Server 2012, for example, you can assign specific IP addresses to the same physical device over and over again to make sure you don't have some of those issues. But again, for things like servers and network printers, you want that same IP address assigned each and every time, whether you do it statically or you use some other approach to make sure that that happens. So DHCP automatically assigns a device a unique IP address, so you're not going to have that issue of accidentally assigning two devices the same IP address. So that cuts down on the management side of things for a systems administrator. DHCP is an application layer protocol. Some of the reasons for implementing it: reduces time and planning for IP address management. You don't have to keep track of what IP addresses you've already assigned, which ones you haven't. It reduces the potential for error in assigning an IP address. That duplication of IP addresses, you're not going to have that issue. It enables users to move workstations and printers. You move your workstation, plug it into a different port in the network, and you're going to be good to go. And it makes IP addressing transparent for mobile users. It's also a problem from a security perspective because it allows people who shouldn't be on the network to potentially connect to the network. So there's a potential problem there. DHCP leasing process: the device borrows or leases an IP address while it's attached to the network. That address, or excuse me, that lease is valid for a set period of time. Usually you can configure that as a systems administrator how long that time is, but you can set that and it expires at the end of that time. You can also manually force a client off the network. As far as configuring your DHCP server, you can set that address range, the lease time. You can also set the range. So you may want to assign DHCP addresses within a certain range, and you can do that using your DHCP server software. As far as the steps to negotiate the client's first lease, it's going to look something like this. So you may have client A here at the top left that wants to join a network. How does it do that? Well, it sends out a broadcast message that says, hey, I need an IP address. Is there a DHCP server on this network segment that can give me a valid address for this network segment? The DHCP server is going to respond to that, says, hey, yeah, I've got this IP address, 123.45.67.89. The client says, hey, I'll take that, I can use that. And finally the DHCP server says, okay, you've got that's your address, that's the one you're going to continue to use until the lease has expired or been terminated. They can expire based on a period of time established in the server configuration, or you can manually terminate it either at the server or by the client. On the client end of things, when you do that IP config, one of the things that you can do is release your IP address. And there's reasons to do this. You may have a bad network connection and you want to reset your network connection. You might want to release your DHCP configuration information. This is basically what happens when you do a repair on your network connection. It's going through that process of releasing your IP address and then reestablishing a new lease. Circumstances requiring lease termination, DHCP server might fail, needs to be replaced, things like that. DHCP services run on several server types, and installation and configures may vary. Again, if it's the DHCP server built into your wireless router, probably going to be relatively simple as far as the options. If it's in a full-blown server such as Windows Server 2012, you're going to have lots and lots of options. Okay, private addresses. We talked earlier about some of the different IP addresses, and we talked about routing them and how there are private addresses that are not meant to be routed across the internet. This is one of the ways that was created to extend the life of IPv4. It basically allows duplication of IP addresses because they're happening within a local area network rather than out on the web. So they're not being routed. So if my home group of private addresses has the same address as one of the computers on your home network, there's not going to be a problem because we're on different segments. And these are referred to as private addresses. So it allows hosts and organizations to communicate across an internal network, and they cannot be routed on the public network. Specific IPv4 address ranges are reserved for private addresses. Link local addresses are provisional addresses capable of data transfer only on the local network segment. Now, there's this relatively new concept when it comes to, and they probably presented these a little bit out of order. For this slide, it's kind of related to the DHCP section we were talking about just a moment ago. So there's zero configuration and a PIPA. Zero configuration is really designed around IP version 6, and it's this idea that computers will automatically be configured across the internet. So you'll essentially be guaranteed that you don't have any sort of duplication of addresses. You won't have private addresses anymore. Everything's going to be part of the internet, and it really cuts down on the configuration issues that we have. It isn't very widely used yet. It's something that's still really kind of in the works, but it is something that's kind of coming down the pike. There's also a PIPA addresses. These are addresses that basically your computer is automatically assigned if you have a DHCP server on your network and it fails and you don't have any other configuration information entered on your local computer. The idea is that all computers on a local segment will use this same segment information, same IP addressing scheme, and thus still be able to communicate. That's in theory anyway. In reality, remember earlier we were talking about it's important to manually or statically put in the configuration information for things like your printers and things like servers. And when you do that, you're basically putting those on a different segment than you are your PIPA computer. So as a result, the computers that are serving the clients are effectively on a different network segment, and thus they won't be able to communicate when your DHCP server is down. So in theory, a PIPA is kind of an interesting approach. In practice, it's not particularly effective. Something else we talked about earlier as well is this idea of ports and how ports are combined with IP addresses to create a socket. So processes are assigned to unique port numbers. A process's socket is a port number plus that host machine's IP address. So when we put these two together, this is what allows a server to be able to manage multiple connections all at one time, because it's getting it's getting web requests from lots of different clients potentially at the same time. How does it keep track of those? Well, they're all coming in on port 80. That's how it knows to respond with the web server, but they're coming in from different IP addresses. So the socket number is different, and so it keeps track of those communications using that socket number. Port numbers simplify the TCP/IP communications and ensures data is transmitted correctly. So for example, a telnet port is port 23, typically, unless you've changed it for some reason. It's not a good reason to do so, other than security. IP version 4 host address is 10.43.3.87, so a socket address is 10.43.3.87:23. So let's go take a look at an example here just real quick. So my home network, home server, does not allow me to host a website on my home network. So what I've done is I've changed the port number for my web server to port 8080. The problem with that is if I designate just port 80, their service is going to block it. They don't allow that. So to get around that, I've changed the port number, and when you change the port number, you have to designate that it's on a different port. So that's what the :8080 is. That tells the web server, oh, I've got a response on port 8080 in this case, and as a result, it responds accordingly. Okay. So here's kind of a graphical representation. You've got a client that wants to go establish a connection. It has an IP address. It sends out a request on port 23. The server gets this request in, and it's going to serve up email. It serves up web pages. It serves up, in this case, telnet. So how does it know how to respond? How does it know that this is not a web request on port 80? Well, it knows because it's coming in on port 23. So when it gets a request coming in on port 23, it uses its telnet software to respond to the client. Port numbers range from 0 to a little over 65,000, and there's 3 general classes of ports, if you will, or port ranges. Well-known ports are 0 to 1023, and these are controlled by the operating system or the administrator. And these are very important ports because these are ones that are typically used by the administrator or by the operating system, and can be a problem if they're not managed properly in terms of being a security risk. Registered ports are 1024 to 49,151. Network users and processors with no special privilege. So these are sometimes referred to as privileged ports. And then dynamic or private ports are the rest of those. So here's some of your commonly used ports, or common ports. Port 20, port 21 FTPs, you'll see a lot. 23 for telnet, SMTP for mail, simple mail transfer protocol, not the same as SMTP. Or, SMTP. And then there's another one. I'll talk about that here in just a second. SMTP, DNS is port 53. HTTP is port 80. POP3 is another mail protocol and operates on port 110. For time, NTP is on port 123. IMAP's another mail protocol on port 143. And then HTTPS on port 443. So those are probably your most common ones. FTP, Telnet, SMTP, DNS, HTTP, POP3, NTP, IMAP, and HTTPS. Those are the ones you really want to focus on. If you happen to be running any kind of remote desktop stuff on Microsoft, at least, RDP is 3389. And to be able to allow some of those accesses, or some of those your servers to be able to use some of these services, or to be able to share these services on the internet, you have to open up these ports on your router to allow the requests to come in. So on my router, I had to open up port 8080. Okay, so host names and DNS. TCP/IP addresses Remember, those are long. Those are those numbers, 68 dot whatever. They're numbers that are long and not particularly easy to remember. You may be able to remember 1 or 2 or 3, but it gets difficult to remember a lot of those. Typically, people do better remembering words, and that's where DNS comes into play. So a host is an individual device. It's your local computer. It can be a server, it can be a router. But a host is a particular device that's connected to the network in some way. The host name is the name that we use to describe that device. What we want to be able to do is to link that name to that TCP IP address, and we do that through DNS, or domain name. The domain is a group of computers belonging to the same organization that shares a common part of the IP address. Domain name identifies that domain. So loc.gov is a domain, and depending on this top level domain, it's going to be associated. It's going to tell us what it's associated with. Is it a company? Is it a university? Is it the government? So clearly .gov is the government. .com is a commercial entity. .edu is a university. So those are all different top level domains, and it tells us what their domain name is. So loc.gov is their domain name. Tarleton.edu is their domain name. Now, a fully qualified host name is not just the top level domain and not just the organization's domain, but also the client or the host's name as well. So blogs.loc.gov is a fully qualified host name. So it's the local host name plus the domain name. So typically you're going to see something like www.google.com. That's a fully qualified host name. Com for commercial. Google is their domain name. The www is actually a reference to the host, to the web server's host, or the web server, the host named www. So the labels or character strings are separated by dots, and those represent the level of the domain naming hierarchy. So for example, www.google.com, the top level domain is this .com part. The second level domain is Google. This is actually this is assigned by one of our naming organizations. Google purchases this particular domain name associated with .com, that top level domain, and then Google manages www, so they manage their web server. They could have just as easily named this web or whatever it is that they wanted to refer to it. The www is just a naming convention. Second level domain may contain multiple third level domains. ICANN has been established domain naming conventions. So we've got a lot of different ones that are out there. ARPA, COM, EDU, Gov, org, etc. And there's lots of others, and there's others that are recommended or considered fairly regularly and routinely denied in a lot of instances. ICANN approved over 240 country codes. So in addition to different organizations, they also have country codes. So each country has their own. So occasionally you'll see something, a government organization here in the U.S. that ends in .us to represent the United States. Host name and domain name restrictions, any alphanumeric combination up to 253 characters. You can include hyphens, underscores, and periods in the name, but there's no other special characters, so no question marks and things like that. Now, host files. In the early days, before you had DNS servers, you had to establish what was known as a host file, and this is what really created the link between domain names and the IP addresses of different machines. And in fact, this is a technique that some viruses use on your computer today to be able to send you to the incorrect web pages. So ARPANET used host file, a host.txt file on your computer. It's a text file that associates host names with specific IP addresses, and hosts are basically matched line by line. So on an individual line, you're going to have a host name, and you'll have their corresponding IP address, and you have an alias for or nickname for for that particular site. This happens both on Windows machines as well as in Linux and Unix-based machines. Have files that serve this same function. So here's basically what the file might look like if you were to open it. It's just a simple text file. You've got your local host address there, so you can test. You've got other ones that have been mapped. So you've got this in right here. This IP address is mapped to www.cengage.com. So when you type it in, the first thing your computer does is not run to the DNS server. If it's enabled, it runs to your host file and says, okay, well, I've got that address in right here. That's the IP address that I'm going to go to. Now, if it's not enabled or it's not entered into your host file, your computer then will go to your DNS cache and then DNS server to check and try to find this. It's going to keep looking until it finds the IP address associated with the name that you've typed in. The way a virus will work is it actually enables your host file to be used, and then let's say, for example, this doesn't say Cengage. Let's say this says Chase, www.chase.com, and instead of using Chase's IP address, they use a different IP address, their own IP address, but they've created a website that looks like Chase. Well, if they're in the business of writing viruses and stuff like that, they're probably not all that concerned with violating copyright and all those kinds of things in stealing Chase's logo and all that kind of stuff. So they create a web page that looks just like it. You go to log in and you type in your username and password. They've now captured your username and password. They simply return an error to you and then redirect you back to the legitimate Chase page, and you're none the wiser. You just think it was a glitch. So that's one of the ways that viruses work. It's one of the ways they steal your information. So DNS is considered a hierarchical naming structure. It associates domain names with IP addresses. DNS refers to application layer service accomplishing association. It's an organized system of computers, databases making association possible. There's also this idea of DNS redundancy. Many computers across the globe are related in a hierarchical manner. There has to be more than one computer that's sharing this information. So there's 23 root servers, and they start to disseminate different domain name information and associated IP addresses down this hierarchical structure. So we've got a slide here in just a second that hopefully will kind of illustrate this process a little bit more, I think. As far as the components of DNS, you've got resolvers, name servers, and namespace. Resolvers are any host on the internet that need to look up a domain. So your client, in a lot of cases, is going to be a resolver. We need to resolve this particular IP or this particular domain name into an IP address so that our packet can get to where it needs to get to. We've got a name server. That's where when we ask for the IP address, that's who's going to give us this information back. It houses a database that keeps track of those IP addresses and domain names and returns that information back to us. And then there's the namespace itself, the abstract database of IP addresses, associated names, etc. Okay, so here's what the process actually looks like. So here's our client here, and we need to access this website, www.loc.gov. Well, the first thing we're going to do is we're going to check to see is our host file enabled, because if it is, that's what we're going to go to. Then we're going to look at our DNS cache. If we haven't already looked up this address in the past, it won't be there. So we're going to have to access our local DNS server. If the address is there, we're done. It's going to give us the IP address. We're going to go straight to it. Well, let's assume that it doesn't. If it doesn't, our DNS request is going to get passed up the line to the next DNS server. This is why it's a hierarchical structure, because if that one doesn't have it, it's going to pass it up even higher. If that one doesn't have it, it's going to pass it up even higher. We're going to go back ultimately until we get to one of the root servers if we have to. And then we'll start to traverse the system and bring back that IP address to our client so that we can access that website. And some of the different types of records, DNS records that exist are A records, 4A records, C names, MX, and pointer records. So 4A versus 4A. We're talking about IP version 4 versus IP version 6. And these are just the basic records that are going to tell us what the IP address is for a particular domain name. Canonical name record, it's another name for the host, so we may have more than one name for the host. Mail servers for MX, and then pointer records pointing to a canonical name. As far as configuring DNS records, for the most part, if you're a consumer, you're simply going to point to your ISP's DNS server and go from there. In a lot of cases, it's assigned by a DHCP server, so it's really relatively easy for consumers. For large organizations, they probably want to configure their own DNS servers. The closer the DNS server is to your clients, the more quickly the web requests are going to occur. So there's a reason that large organizations want to maintain their own DNS servers. Like I mentioned, if you're an individual, you may occasionally want to bypass DHCP and actually manually configure your own. There's some steps in the book on page 172 to 173 that talk about this. Personally, I like to configure DNS servers to use multiple organizations' DNS servers, your ISPs, Google's, for example, because that way if a particular DNS server goes down, if you've got another organization's DNS server in there as well, you've got a nice backup. And so it's nice when it's more than one organization's DNS server. And there's a number of public DNS servers that exist, as I mentioned, Google, for example. Now there's also dynamic DNS, and this is something that I use as well for my particular website. I just have a consumer-based IP address. It's at home. It's not a commercial one, and so as a result, my router is configured via DHCP by my ISP. But what happens if I have an IP address or I have a domain name and my IP address lease expires and I'm assigned a different address? Well, now that relationship between my IP address and my domain name changes, and I either manually have to go in there and change it, or I can use a dynamic DNS service. And that's what I end up doing. I use it, for me specifically, I have a D-Link router that I use, and the dynamic DNS service allows it to automatically check in periodically to verify the IP address and reassociate it with my domain name. And so that's basically what dynamic DNS is. As I mentioned, larger organizations do have commercial accounts, and as a result, they typically have statically assigned IP addresses. They don't have that kind of issue. The chapter finishes up talking about application layer protocols, and these work over TCP or UDP plus IP. These operate at the higher end of our protocol stack. These are closest to us, and these are the ones we're closer to dealing with. As I mentioned earlier, when we work with a web browser, we're typing in an HTTP address in most cases. So it's closer to us as an individual. DHCP is another example of an application layer protocol that automatically goes out there to obtain addresses. And there's other application layer protocols as well. Telnet's one of those. Telnet's an application layer protocol that you can use to remotely log into a client, for example, and issue commands. It's extremely useful in server environments and certain types of network components like routers and switches to be able to configure those as well. Drawback to it is it's notoriously insecure. It's not encrypted. Your communication is not encrypted, so everything can be captured if anybody's listening in on the communication. So that's one of the real problems with Telnet. FTP is also notoriously weak. Everything's in clear text again. There is secure FTP, but that's a little bit more recent. But file transfer protocol is a protocol, application layer protocol, that's designed for the efficient transfer of files from a client to a server or vice versa. Basically, you're going as a host, you're going to access an FTP server, and depending on how that server is configured, it'll either require you to log in or it'll allow anonymous access. And then again, depending on how it's configured, you can either upload files and or download files. And if it's a text-based FTP server or client, a lot of this is done via text. Trivial file transfer protocol enables file transfers between computers. It's a little simpler than regular FTP, hence the trivial aspect of it. It relies on UDP, so it's connectionless, so it tends to be more efficient. It's very fast, but again, it does not guarantee reliable data delivery. No security is involved. There's no password required or anything like that. There's no directory browsing, so typically you have a folder on an FTP server allows you to browse that folder and drill down into subfolders. You don't have that with TFTP. NTP, Network Time Protocol, is another application layer protocol, and this is designed to keep all the clients on a network and the servers, for that example, and some of the other networking components, all consistently timed. And the reason this is important is we have a lot of log files that require or that log the time when various events occur. If time is not properly set, we run into a problem. So time synchronization is a big deal. Ping is another application layer protocol, and this is a valuable one, especially as someone that's doing network troubleshooting. Ping allows you to verify that connection, allows you to check your local protocol stack like we did earlier. It allows you to check the DNS server when you ping an IP, a domain name as opposed to an IP address, and it resolves the domain name to an IP address. That tells you that DNS is working properly. If you were to ping an organization's IP address and get a response, but ping their domain name and not get a response, that tells you that there's a DNS issue of some sort. So here's an example of that ping request again that we were talking about. So you ping an IP address, you get a response, and in this case they don't get a response for that IP address. So to kind of summarize this chapter, what did we talk about? We talked about protocols defining standards for network communication. We talked about TCP/IP in depth. That's really the most popular suite that's used. We talked about TCP being connection oriented. We talked about UDP being more efficient and connectionless. UDP is more efficient because it has less overhead. So it's really worried about, let's just get data from point A to point B, and we hope it gets there, but maybe it doesn't. We talked about IP providing information about how and where to deliver data, so we're talking about IP addresses. IP version 4 is unique 32-bit numbers. IP version 6 composed of 8 16-bit fields, so a lot more complicated addresses. We talked about DHCP being used to automatically assign addresses. Helps people manage their networks a little bit easier, more efficiently. Can be a little bit of a security concern in that it might allow people to just kind of randomly connect to your network. So there is that potential security issue that you need to think about. And then we talked about DNS tracking domain names and their addresses. So linking together a web address to the IP address, because computers talk in terms of those IP addresses. We don't. We need domain names. So that's what the purpose of DNS is to tie those two together. So that is this chapter in a nutshell. This is a good chapter to go through. You really need to know a lot about TCP/IP. There's another chapter that goes into this in a little bit more depth, and we'll talk about it more when we get to that point. Until then, if you have any questions, let me know. Follow me on Twitter at Schuessler PhD. And other than that, let me know if you have any questions. Take care. Have a good one.